We have done angle between two planes, we have done angle between a line and a plane. Now we are going to do the concept which is finding the point of intersection of a line and a plane. Okay, to find the point of intersection of a line and the plane, it's easy to find the angle, but finding the actual point of intersection is a bit difficult. Again, we have three patterns for plane. Line, you have again three forms. Now, in whichever form they are given, you should be able to find the point of intersection. That's the concept here. Okay, what you are supposed to do is, whichever form is it has been given, try to put them all into vector form. Okay, so that means you are only using this and this. This is one method for finding the intersection of a line and a plane. Let me take a direct question with vector form. Okay, so if I have the plane as 1 1 minus 1, and this is what is given for the equation of the plane, and I have equation of the line to be in vector form. I'm assuming that we have already come to the vector form of whatever question has been given. Okay, we have changed the question to vector form for both. In this case, what do you do first? So you have to make three simultaneous equation for this. Like you should say x is equal to 1 plus 3m plus 3n, and in this case x would be equal to minus 3 plus 2s, and y equal to and z equal to, right? You'll get m and n here, and you'll get in s here. So you have three simultaneous equations, in fact six of them, but you can actually, you have m, n and s to be solved. You can equate this to this, that is, you can equate 1 plus 3m plus 3n to be equal to the x of this, which is minus 3 plus 2s. Okay, and y of this to y of this, and z of this to z of this. So you'll get three simultaneous equations in m and n and s. You can solve them in any way you like to solve it. You can use your GDC matrix method or any method. Once you solve, you'll be getting the values for m, n and s, right? So you need to just substitute in this m and n. You substitute m and n here once you get them, and then you substitute for y, and then you substitute for z. So you'll be getting x, y, z for the plane, right? And then in order to check whether this x, y, z is the same, they just substitute in this and check if you have the same values of x and y and z when you substitute the value of s that you got by solving the three simultaneous equations. If they are not the same, then the point of they don't meet. Okay, if your xyz doesn't match with the xyz when you substitute for s here, then there is no point of intersection. Okay, say for example you are given an equation of this type. Okay, x plus 3y plus 5z equals 32, and can you convert this to r dot n equal to n dot a? Yes, it's easy because n is 135. We have done this already, and this side should be 32, and here it is r, right? This is how you change this to normal form. And if the equation of the line is this, z plus 2 over minus 3, then the normal is the direction vector is actually 2 1 minus 3, because you can take this as y minus 0 over 1. Okay, and the point A would be 2 0 and minus 2. It is got from these points, right? 2 0 and minus 2. So this is vector A and this is vector B. So you need to put lambda and you need to write this. Okay, what you do is you can write this as 2 plus 2 lambda, 0 plus lambda, minus 2 minus 3 lambda. Okay, so this is the r for the line. So substitute this r into this way, that is 2 plus 2 lambda. This is another way of finding the point of intersection. Okay, dot 135 equals 32. So what you're doing here is go back to this and substitute lambda equal to 1. So your r, which is x, y, z, would be equal to 2 plus 2 is 4, and 0 plus lambda 1 is 1, and minus 2 minus 3 is minus 5. Okay, so the point of intersection is 4, 1, and 5. So this is how you find the point of intersection of a plane with the line. This is a plane and this is a line. So plane and line were given in Cartesian form, and this is the way you solve them to find the point of intersection. Okay, you can also use another method. Say if the plane is given in the Cartesian form like this, and the line is given in Cartesian or any other form L, you can actually change this to parametric form. X is equal to x1 plus L lambda, right, or LT. Let me use T is easier. Y1 plus MT for Y, and Z1 plus NT for Z, and substitute the values for X, Y, Z from here. That means you'll have A times x1 plus LT, etc., equal to D, and you solve for T. Right, once you solve for T, substitute in each and you can find what is X, Y, and Z. So this is another way of finding the point of intersection of a plane and a line. How do they meet? When two planes meet, they meet on a line or they don't meet at all. You can have two planes parallel to each other, or you can have two planes meeting on a line. Okay, so you can see that this is how they meet, and this is the line of intersection. Now what is the intersection between two or more planes? Okay, now we are going to discuss about how two or more planes intersect and how to find the point of intersection, point or points of intersection if they meet at all. Okay, now for this you need to always have the planes in Cartesian form. Again, for this you need some other concept called augment matrix, and you should know this. If you don't know, please go back to matrix chapter and refresh these two concepts: row reduction using augmented matrix. Okay, these two are very important, though you can use GDC, but there are certain cases where you cannot use GDC because some of these numbers would not be given and you need to find them, for which you cannot use GDC. You need to do row reduction manually. Okay, so the augmented matrix for this would be A1 B1 C1, A2 B2 C2, A3 B3 C3, and you do this. Please go back to matrix chapter if you are not thorough with this. Okay, and then you need to do the row reduction, and you need to simplify to this format, and you might have some numbers like say R, S, and T. Okay, so if it is in this form 100010 and RST, then the point of intersection is nothing but the values which you get in the last column, RST, if you are able to bring it to this format. But if not, if you are not able to bring this to this echelon form, then what happens? Then you should concentrate on the last row. Say this is case 1 where you can actually make it to the row, the echelon form, which is 100010001 form. In that case you have a unique solution, which is one particular single point. Case 2 would be when you cannot bring it to this echelon form. So what you do here is you concentrate, you don't bother about the other rows, you concentrate on the last row and try to get as many zeros as possible, and 000 on the last row with or without a number here. Say I have a N, I have some L, and I have a M here. So this means that 0 equal to N. Okay, which shows that there is no solution. You can't have 0 equal to N, right? So there is no solution, which means that the planes are parallel to each other. Okay, they do not intersect. Fine. In case 3, you concentrate again on the same last row, 0, make it maximum number of zeros there, and in case if I have L, M and a 0 here, then you get 0 equal to 0. This is true for any values of x, y, z, right? Therefore, you have actually infinite number of values for x, y, z, which means the planes intersect on a line. Okay, when you have this format 0, 0, 0, 0, there are infinite number of solutions. Please don't stop with that as an answer. You say that the planes intersect over a line. Okay, because you can understand that when the planes meet on a line, you have many points, infinite points of intersecting. Okay, and when you have this format, there is no solution, the planes are parallel. Okay, you cannot have solution on this. Okay, another important point here is, if it is in case 1, you will be getting the determinant of A not equal to 0. What I mean by determinant A is, this is called A, like matrix A. This determinant would not be equal to 0 if you get a unique solution. Okay, or in other two conditions, you cannot use determinant A because it would be equal to 0. In this case, you can actually use x is equal to A inverse B to find the point of intersection. Okay, because A inverse exists because modulus A is not equal, determinant of A is not equal to 0. But in these two cases, you cannot use this A inverse B technique because determinant A would be equal to 0, therefore you cannot find A inverse. So when determinant A equal to 0, then you have either one of these cases, no solution case or infinite number of solutions case. Okay, you just need to use your row reduction technique and bring it to this form, and then you have to say which one is true. So why did I say that you might not be, sometimes you might not be able to use GDC? Say if a question has a number there and you are given that it does not have solution, then if you are not given say 2x plus 3y minus 4z equal to 3 and x minus 2y plus z equal to 4, and you are given like 2x minus y plus some say for example some lambda z equal to 6. So and you are given that these three planes do not have solution. Okay, so what you need to do is, they don't meet, right? That's the question given, and hence find lambda. So I'm just giving you what the method, I mean I'm not going to solve this. What you do is you need to make the augmented matrix here. With this you can see that there is a lambda, therefore you cannot use GDC to in order to reduce it. Okay, so use your manual row reduction techniques and try to make the denominator, I mean the last row, as many zeros as possible. See that you bring this to 0 0 0, and then see you should be having some number, and here you'll have some, you cannot make this 0 because it's in lambda, right? So you'll have some, say for example you have some 5 minus lambda, and you'll be having a number here because it says it's no solution, right? So you'll have a number, say you have 6. Then what you need to know is, since there is no solution for this, you should not have a number here, right? It should be a 0. This position should be a 0, which means that 5 minus lambda equal to 0, therefore lambda equal to 5. Okay, again I repeat, it may not be the same, you may not get 6 here, you may not get 5 minus lambda here, but I've not done the actual calculation here. I'm just giving you an example. If on row reduction, if you get this value in the end, then you stop there. Once you get two zeros here and a number here, stop there, and you can say that 5 minus lambda equal to 0, therefore lambda equal to 5. Okay, so again I insist, why I insist on this is, you may not be able to use GDC for all types of row reductions. So it is very important that you know how to do row reduction of a matrix. Okay, so please go back to matrices and learn how to do row reduction. Finding the distance, shortest distance between a line and a plane. Okay, so if you have a line, a plane, and if you have a point, say x1 y1 z1, it's given, and then you want to find the shortest distance from this point to this plane, which would obviously be the perpendicular line to the plane, right? So we know that the perpendicular line is nothing but the normal vector. So there is something to do with normal vector here. Okay, so we need to find the normal vector first. Okay, so find the normal vector. Okay, whatever form it is, you need to find the normal vector, because if it is in Cartesian form, it's just ABC from x from the values of ax plus by plus z cz, and if it is in vector form, it's b cross c, and if it is a normal form, yeah, it's easy, you can directly get the n from that. Okay, so in either way, in any of these ways, you just find the vector which is normal. Say I have ABC in this case, a normal vector ABC, you find it out. Now you need to find the normal vector, the vector ABC passing through the point x1 y1 z1. Okay, so ABC is, now this is the direction of this line is n vector, and it passes through the point. So you know that if a line has a direction of n and passes through the point x1 y1 z1, then from the equation of the line, it's like x1 y1 z1 plus lambda n, right? It was a plus lambda b, and here b is n, because n gives you the direction of the line which we are considering. Okay, this line. Okay, now so your line, which let me call this as p, and let me call this as some x. Okay, so px or xp would be x1 y1 z1 plus lambda times a b c. Okay, you can write again it, you can write it in any way you want. You can express this in parametric vector form, whatever it is, depending on the question. Okay, so now you need to find the point of intersection of this line with the plane. This we have done. Now you have a line, you have the plane. Plane's equation would be given already, because without the plane's equation you cannot find the normal. So you have found the normal from the given equation of the plane. So you have, say I have r, equation of the plane, and equation of the line is xp. So I have the plane, I have the line, and you know how to find the point of intersection, right? Just now we did that. Whatever format they are given, you just need to find the point of intersection of these two. Okay, so this point of intersection of the line, of this line with this plane, would be this point x. Okay, this is also called the foot of the normal to the plane. Okay, because this is the normal, and this point x is foot of the normal to the plane through the point p. Okay, so this is what that x means. Now you need to find, you know, the point x, you know the point p, which is x1 y1 z1. Now you know the point x, say I have x2 y2 z2, and then you know how to find the distance between these two points, right? Root of x1 minus x2 the whole square plus y1 minus y2 the whole square plus z1 minus z2 the whole square. Okay, so this is what you are finding to find the distance, the shortest distance from the point p x1 y1 z1 to the plane. Okay, now if you are given two planes, that is, if you are asked to find the shortest distance between two planes, right, two parallel planes or two planes, whatever it is. So what you do is, say you are given a1x plus b1y plus c1z equal to d1. I'm just taking it in Cartesian form because it's easier that way. Now I think by now you know how to interpret any form into the other, right? If these two planes are given, you need to find the shortest distance between these two planes, right? So but you know how to find the shortest distance from a point to a plane. So it's easy, just take one of the planes and find a point. Say I take this and I find a point, like I substitute x is equal to y equal to 0, and I find what's z. So that means I'm finding the point 0 comma 0 comma z, right? So this point would behave like the point p that we did here. Okay, so once you find the point and once you know this, now you can find the shortest distance, which should be the perpendicular distance from that point to the plane. Okay, I think that should be very easy now. Let me do one small question for you. Find the shortest distance from the point 2 minus 1 3, which is point A, to the plane, which is x minus y plus 2z equal to 27. Okay, now what was the first step? The first step was to find the normal. So the normal is 1, -1 and 2 here, right? The second step was to find the line passing through the point. This was equal to n is this. So this is the direction vector of the line through A. Okay, so our line would be, the equation of the line would be 2 minus 1 3 plus lambda times 1 minus 1 2. Okay, this will be the equation of the line. This is what we did in this place, right? We have found the equation of the line. Now what do? You know the equation of the line and we need to solve. So this would be x is equal to 2 plus lambda minus 1 minus lambda, and z equals 3 plus 2 lambda. Okay, all you need to do is substitute this in this and find lambda, and then substitute and find the xyz of for the point of intersection. Hope it was helpful. All the best.